The next topic is about free energy principle and also predictive coding, first given by a short lecture on these concepts by Ryota Kanai and also Yuki-san mo harasu? Okay, and Yuki Nagai.
Okay, so so this session is about predictive coding, but I need to clarify what it is and also my position about this theory. So actually I didn't do, well actually I did some preparation for this talk, but then last night I mentioned my slides are too complicated and everyone will fall asleep, so I decided to give a completely different talk, so I don't know what I'm going to talk about. But actually he's right. So I gave a tutorial on free energy principle at ASSC in Beijing very recently. So initially I had a full room of people very interested in learning about this theory, and then after the break, about half of the people disappeared. So I have to be careful. Anyway. So maybe many of you know that I'm running a company called Araya, where we work on consciousness. Of course, we do business side of things, but half of the company is trying to create artificial consciousness, and we work on many different things. For example, Autism and Kitazawa-san, they're working on IIT, and many of us are now interested in intrinsic motivation for the reason I'm going to discuss today. And some of us also work on free energy principle and so on. And so I believe these different approaches may facilitate our understanding of consciousness. So in a way, it's a constructive approach. And but basically, as a company, we have to create consciousness. Otherwise, we will bankrupt. I don't know how we can sell qualia. Once I thought about patenting qualia, but then the patent officer used to solve the hard problem too. Anyway, so when we talk about creating consciousness, there are two issues. So one is a practical issue. So what do we need to achieve functionally to claim that we have created consciousness? And then the other one is, okay, once we created something that looks like having some consciousness from an external viewpoint, how can we prove that it has consciousness? So these two corresponds to the concepts of access consciousness, so apparent consciousness, and more the phenomenal consciousness. So for this part, our approach is to use some variants of free energy principle or predictive coding, or as I argue later, as long as the system has internal model, generative model, then at least in my view, it has a chance of having some conscious experience. But then we can use IIT to analyze whether such systems have high degree of integrated information or interesting conceptual structure. Okay. Let's skip this. Okay. So these are the two main things. So for creating consciousness, we use free energy principle, or at least we thought about using free energy principle because, so the idea is, according to Carl Friston, what the brain does is to minimize something called free energy, which is an information or some sort of error term, but to perform all kind of cognitive functions. So this is kind of useful for implementing functions. And since the brain has consciousness, or if we manage to create something like a brain, then it may have consciousness. But then we are also working on IIT to prove the presence of consciousness in artificial systems. Okay, and so this morning now I'll show the 2x2 table based on this Tim Bergen's 4 questions. So when we ask why questions about biological properties. We can ask these 4 properties. And yeah, so IIT is mainly about mechanism. So how the brain generates consciousness and what's the minimum necessary and sufficient condition for consciousness. So that's the kind of causation question. But predictive coding or other like statistical inference methods give us some idea and also conceptual vocabularies to discuss how our brain learns to capture statistical regularities in the environment and then model it. So yeah, so in a way, a free energy principle or predictive coding give us like different kinds of framework to think about why we have consciousness, or for example, why like a visual experience feels different from auditory experience. Okay, so according to the program, so this is the main question. So the question is whether predictive coding is relevant for understanding consciousness. And so I'm supposed to argue for the relevance, so I'll try. But when we discuss like relevance of predictive coding or free energy principle, more generally, we have to distinguish these 2 kinds of questions. So one is, the first question is about relevance. Okay, so maybe I should first explain this. So free energy principle is just one version of many possible statistical learning. And then predictive coding is one particular implementation of free energy principle. So it's a like very small subset. But I want to start from somewhere broader, which is I want to start from whether statistical learning is important for understanding consciousness. And my answer to this is yes. But I don't know whether free energy is correct or predictive coding is the right kind of implementation happening in the brain. So these are separate questions. So we can ask about the mechanisms, and for these, we can test with neuroscience whether these like specific theories are correct. But I think when we talk about the relevance of such concepts, we have to start from here. Okay, so first about the relevance. So the first question is, okay, so do you agree that how the brain represents the external world is relevant for phenomenal consciousness? So, for example, when we talk about phenomenal experience, we talk about redness of red, and that depends on how the brain represents color. That seems very trivial to me, but yeah, but if you accept this,
But do you want to ask the audience?
okay, so do you agree? Yes? Okay, keep your hands up. All right, so the second question.
But you should ask also who does not agree.
Oh, okay, who does not agree with this? Nobody. Okay, so let's see like if anyone changes opinion after the debate. Okay, the second question is when we talk about, okay, we have some qualitative differences in the experience of like visual stimuli and auditory stimuli, and in my view, they come from differences in statistical regularity in the visual input and auditory input. And so that, yeah, so this phenomenal difference reflects the difference in the input statistics. Do you agree? Anyone disagrees? Okay, so that's good. Okay, the final thing is, okay. Yeah, so do you...
Sorry, before that, what do you mean by reflects?
Reflects? Okay, so... Okay, so maybe it's related to the third question. So here I'm assuming that, okay, so the brain somehow learns this kind of statistical regularities. And that's reflected in maybe different kind of dynamics or connectivities in the brain. And then those differences in the brain give rise to differences in experiences between vision and sound.
So the question is maybe it reflects means it is the only cause or the partial cause.
Partial. Yeah. Yeah. So for example, yeah. So the reason why I said partial is, for example, if someone is born, okay, let's say the brain is already hardwired to process visual stimuli or auditory stimuli, then they already have some sort of internal model. And then the system doesn't have to learn anything, it just has the model, so then it can immediately, have that experience. So in this case, any exposure to statistical regularities is unnecessary. Yeah, so the third point is kind of the same, so I'll just skip this one. Okay. And then about the mechanisms, okay. Well, what did I write? Okay, so the brain learns to represent the external world through some information measures. So it's again like statistical regularity. So the brain learns statistical regularity or some like information structure. Do you agree? Yeah. Yeah, maybe I like intentionally made this sound like really trivial, but I think these are like really like initial motivations. Okay, and so well then the more specific question, then does the brain learn regularities with some sort of approximate statistical measures? Do you agree? Yeah. Yeah. No.
What is with me?
Hmm? What?
What is with me?
With
It learns it by
regularity with
like using the statistical measure as some kind of optimization.
yeah. So
Variational base or something?
yeah, I was thinking like yeah. So the last one is a variational base. So do you think the brain is using variational base?
It's,
This one.
but there might be other approximations to Bayesian inference than variational.
Well, the reason that it doesn't have to be Bayesian, right? It could be that some sort of non-Bayesian inference. So the brain doesn't have to do like any Bayesian, but it just reflects. It just.
So Bayesian would be a statistical measure.
Well, okay. Yeah, but in my category, Bayesian is kind of specific kind. So for example, it's commutative, and but for decision making and things like that, we can think about non-commutative probabilities. Yeah, so in a way, I think the claim that the brain is doing some Bayesian inference, it's a kind of strong claim, because because it means like it doesn't have like any cognitive bias and so on.
It's much stronger than
Just any
approximate Bayesian.
yeah. Okay. Maybe like more specific version is okay. So I don't think the brain is actually doing Bayesian inference, but there might be it might be doing some sort of approximate Bayesian inference, and that's my view. And that's something I wanted to convey by this sentence. Okay, but anyway, I haven't defined what like Bayesian inference is yet, so okay, I'll just skip this. Yeah, but my point here is like sometimes I'm running out of time.
No. 15 minutes.
15 minutes, okay. Yeah. Well, my point here is, okay, so when we talk about or criticize predictive coding, the first point is we can discuss whether it's a useful framework to think about when we think about how the qualia or experiences are shaped through experience, so that's one point. But then it's a separate question to ask whether it's actually happening in the brain, because a lot of times like we really struggle to find like prediction error signals in the brain as we expected through neuroimaging and so on. But my point is probably like criticizing specific implementation is not so relevant for this debate. Okay. Okay. I finished half of my time already, so yeah. So then I'll just spend the rest of the time for maybe a few more slides. Okay. So I wanted to explain why we should care about whether the brain does inference or statistical inference. So that's the main point, and I think that's the most relevant for the question of whether predictive coding is relevant for understanding consciousness. But then I feel I also need to explain a little bit about what free energy principle is and what predictive coding is. So I don't know if I have time for this. So I'll try to give you just a flavor of that. And then finally, I don't think I have time for this, but I could show that predictive coding is a special case of free energy principle. So it's a subset. But for example, we could use something like variation autoencoder to perform something equivalent to free energy principle. So in terms of implementation, there are many ways to implement free energy principle. And so in that sense, in terms of relevance, the specific implementations are not very important. Okay. So the first point about the relevance or motivation is that I feel we need to explain the structure of experience. So as I said, it seems like we have distinct, qualitatively different feelings about visual experience and auditory experience. And so that needs to be explained. And we also need to explain where that kind of structure or also subject, phenomenal differences in auditory and visual qualia come from. And also a bigger question is, we culturally talk about representation. And what is a representation? So that's, so when we think about free energy principle or machine learning in general, we can gain more specific ideas about what a representation means. Okay. Then the second motivation is it's actually kind of similar to IIT. So when we think about the brain doesn't have direct access to the environment. So everything we experience comes through sensors, like images on the retina, but nothing, or the sound and so on. But the brain cannot directly reach what's out there. So basically, we have everything we have in terms of information subjectively comes from some sort of inference made based on our peripheral senses. So that means there's some sort of inference processes about what's causing this particular sensation. And then to make that kind of inference, we need to have some sort of a generative model of the world. And then we experience, for example, redness of red because our brain interprets the sensory signal through that kind of model. Yeah, so without the model, there's no meaning. So in that sense, statistical inference by the brain gives us a sort of conceptual vocabulary to think about how this kind of subjective models are constructed. Yeah, and another thing is, so some people mentioned embodiment or environment. So I think the importance of body and the interaction with the environment is so highlighted by the sort of internal model that connects our own action to the feedback from the environment. So Now, of course, like from the perspective of IIT, as long as there's some sort of like integrated information in the brain, there might be conscious experience independent of like what's happening in the external world. But our experiences are meaningful because we have a model of the world through our interaction. So, in that sense, yeah, we need to have this kind of like agent kind of perspective to understand how an organism forms an internal model and then situate itself in the environment. Yeah. Okay. And let me see. Yeah, so this is some sort of like a taxonomy I thought about. So, okay, so my claim is we need some sort of, okay, the brain must be doing some sort of statistical inference using some internal model, and then like Bayesian inference is one way to do it, but it can be also like non-Bayesian. And but for like Bayesian inference, calculating the posterior is generally very difficult, so there are some like useful tricks called the variational method. So basically, the free energy principle proposed by Carl Friston claims that the brain is doing variational Bayesian inference using Laplace approximation, which derives the predictive coding. But of course, we can do like other like inference methods like MCMC and so on. So, and actually, like there's even like a Wernicke library paper that suggests the brain might be doing some sort of MCMC-like computation. Yeah, so I'm not committed to this predictive coding per se, but I'm more like around this domain. So yeah, so actual implementation doesn't really matter, but I think we need to be able to find some sort of like internal model in the brain or in any artificial systems, and then I want to connect that to consciousness. Okay, so maybe a lot of things I said may sound vague, so I inserted this kind of like very simple figure so that like you get some idea what statistical inference is. So maybe many of you are familiar with like fitting a curve like this. So you have data, and then you have a model function, for example, linear, and then this model has like two parameters, and then you try to minimize the, for example, mean square error to fit the curve. So basically, this is like this is typical curve fitting. But inference is more or less the same thing, but you get a cloud of data, and then you have some sort of like a model, generative model, which has a few parameters. In this case, if it's Gaussian, two sets of parameters, and then minimize the prediction error. Yeah, so minimize this quantity surprise. So it's basically same concept as curve fitting, and then you fit parameters to minimize the error. So that's the same thing, but then free energy is one particular way of doing that. But my claim is basically the qualia or subjective quality comes from the kind of model we have. So in this case, okay. So even if the data are very different, if we end up with the same set of estimated parameters, then we must have the same experience. But the quality is shaped by the shape of the model.
So what do you mean by model shapes quality?
Yeah, so for example, like if you are just a Gaussian fitting brain, then all you can experience is just this Gaussian. But if you have like many models or more complex models, then that's all you can experience. Does it make sense? So maybe so these are the. Okay, so I found this. Okay, so basically a variational basis like this. So you have some sort of like a variational density like this Q, which you're trying to fit to the data, and then this is Okay, so basically you fit parameters within this. Okay, so why you want to know why it's qualia? Why I say?
So I just didn't get the meaning of model shapes qualia. So is it just a blunt statement of saying that we're relying on the internal model? Is that what you want to say?
Yeah. So the structure of the internal model
Is what we
is everything there is. Determines, yeah.
So what does loss function there does?
Oh, in this case here.
Yeah. What does
Okay, so here it's a minimum. It's a posterior.
So that's the error, right? That is a fit and there's an error, right?
Yeah. So you fit this, but to minimize this loss, you optimize these parameters.
Oh, so you're changing the model itself from the loss function.
You move the modes to find the mode of the data. So these two are like generally like optimized through some sort of gradient descent or something like that. 5 minutes. Okay, maybe I'll just mention. Okay, so since I have 4 minutes, I'll just state what I really want to say. So my feeling is that predictive coding by itself is not enough, and so I'm currently proposing that information generation based on the generative model is a consciousness generating processing, and so that takes some time to explain, but finished. Okay, maybe let's stop here. Okay, give me, if I can find that. Maybe something like this. Yeah. I still have 2 minutes.
Maybe you can just tell us.
Yeah. Oh. No.
You can just explain with that, right?
Yeah. Okay, so so when we think about a model, okay, let's say information comes through the retina, and then in the visual cortex, through many layers, it's compressed. So through this, typically we speak of this as some sort of information processing or visual processing, but in my opinion, this is unconscious. But information is generated, for example, like in modern neural networks, there are many ways to generate realistic images, right? So when you have this kind of generative model, in the case of something like autoencoder, you start from like a latent space where information compressed, it could be like labels of some images and so on, and then you can generate maybe realistic face. So that's a generation process. But then this is just neural network example, but when we translate this into predictive coding framework, information processing is bottom-up information compression. So that's unconscious. And I think that's in line with many physiological observations. But when the top-down signals go to earlier areas, so basically this is prediction in predictive coding framework, I think that prediction generates consciousness. And I think there's an asymmetry between this kind of data compression and data expansion. And so my claim is information generation corresponds to this kind of data decompression. And then I think that's what generates consciousness.
So is information decompression similar to what people call readout?
compression is encoding.
No, decompression. So you said it's similar to readout. So
Yeah, it could be readout, but it's more like yeah. I think it's called
readout.
it's called decoding, decoder.
So you compress it right? So you make an abstract form and then you put it back to the original space or something, right?
Yeah. So this part is compression,
Yeah.
and it's also called encoding. And then in free energy terminology, this is like a variational density or recognition density. And then this part is information generation, and I think this generates consciousness, and that's related to generative model. And yeah, maybe I'm running out of time, but I think I'm interested in this kind of idea because once an agent has the ability to generate information counterfactually in the sense that independent of the input currently happening to the agent, then that sort of simulated feature can be used for action selection and planning. So I think that really links consciousness as I defined it to functional advantage. Yeah, so
the simple question is, what is output for the process?
the final output is similar to the input. So basically, like if you have like an image of like faces, then we want to train this network to be able to generate a lot of faces.
Okay.
Well, anyway, so yeah, I've run out of time, so maybe let's discuss more later.
Yeah. Thank you. It's a bit of the short of explanation, but Yukie will give us another kind of perspective on how the predictive coding can be related to consciousness, so that may be good in its own. So let's see. If there is any comment or question about Ryota's thing right now, maybe we can. Yes, Kitaru-san.
Okay, so I have a question about you mentioned something about dynamic things. So at what level and what kind of dynamics you assume for the basis of the statistical inference?
Okay, so yeah, I have an idea about this. So whenever we talk about like statistical inference, we start with like generative models and so on. But then that's always from extrinsic viewpoint. So we want to define what the internal model is based on intrinsic properties. And well, for example, if I like sort of go through the like typical like variational Bayesian inference, then eventually what happens is we have dynamically moving parameters in this sort of information geometry kind of space. In that manifold.
Like an attract or?
Yeah, so I think internal models are we often define from an external viewpoint, but I think all there is in the brain is just dynamics. So I think we should be able to find a mapping between dynamics and a model. So yeah, so that's my current intuition.
Okay, thank you.
Great. Let's move on. Yeah, please.
Thank you very much. So Kanai-san has talked about the general principle of the predictive coding and the free energy principle, and I'd like to show you their implementations for the robots, but not directly the consciousness, but what we are looking at the robotic, the cognition, the cognitive mechanisms. And to make my standpoint clear, I put their take-home message slide at the beginning. So what we are doing, or what we have been investigating, is that how the predictive coding can account for the cognitive development or cognitive mechanisms in robots. And actually, the consciousness is still a new topic to me. As you can imagine, that the consciousness is, of course, a very challenging topic for the neuroscientists and for philosophers and psychologists, but also the very, very challenging or even the very dangerous question or dangerous issue in robotics. because the robot, many people don't believe that the robot can have the consciousness or something. So what we are designing is that there are cognitive mechanism in robots. And then we believe that, we suggest that the predictive coding is a more powerful method or the theory which can account for the different various dynamics in the cognitive development. So I will explain that how the predictive coding ideas can be implemented in the robotic systems, and then how the robot can acquire the various cognitive behaviors. And there, of course, the relation to the consciousness, my suggestion or my hypothesis about consciousness is that the consciousness, the function of consciousness may emerge as a byproduct of the development of cognitive functions. As I said, we don't design consciousness itself. We don't intend to design the consciousness itself, but through the development of the cognitive mechanisms, we may observe their consciousness-like phenomena in our system, our neural network models. So I'd like to discuss with you how our robotic systems can be observed from the viewpoint of the consciousness. So to start with, I'd like to show you their interesting videos which suggest that whether or when their infants start having their self-consciousness or self-cognition abilities. So this is a very famous experiment called the rouge test or mirror test. And in this experiment, experimenter put the red rouge on the top of their infant nose. And the question is whether the infants can try to remove the rouge from the nose. If they can recognize themselves in the mirror, they can of course try to clean it. But then, as you can see that these infants are still too young, so they don't try to remove the rouge, but rather they try to find, for example, another friend behind the mirrors, or they just stare at the mirror, so they cannot really recognize themselves in the mirror. So from this experiment, the psychologists say that their 40-month-old infants are still too young to recognize themselves. Again, here the psychologist also doesn't say that it's about self-consciousness, but the abilities of the self-cognition. But interestingly, in another psychological experiment, researchers found that at the same age, 14 months old, the infants can already communicate with the others well, and also they can help other persons. So in this experiment, the person tries to put their books in the shelf, but then he could not achieve it. So while observing this behavior, the infant just came too close to the experimenter and then help it. The important point here is that the experimenter never looks at their babies, or never provide any social signals to the babies, or never provide any food or drinks or something even after the infants help them. But then they suggest that from these kind of behaviors, the infants may already have their abilities to, of course, to recognize self and also recognize other persons, so that kind of the social, the interpersonal, their self abilities already exist at the 14 months age. But then, of course, from these two experiments, you can see that there is some inconsistency in their findings. If you look only at the behavioral levels, you cannot really know whether the infants already have the self-abilities or self-cognition abilities or self-consciousness or not. On one hand, they say that even at 14 months old, actually only at the 24 months old, infants can pass the mirror test. But on the other hand, the infants can already help other person at 14 months. So why they can do it even without the consciousness about the self? I think that...
Sorry, I'm very naive question about the rouge test.
Yeah.
I think this is mirror cognition, not necessarily self-cognition.
Yeah, it's a kind of extension or a bit harder problem than the self-cognition. They can also have their more simpler experience, just observing their own body directly without the mirrors. In that case, the infants just can pass the test much earlier, like 6 months old or something like that. Of course, this is a bit harder task. That's why their ages have the differences.
Because I think philosophically this is a different thing. the self as itself and self as a member of humankind is a different notion. I myself, and I as a member of the society or the humankind is a different level. So it is philosophically natural, I think.
Yeah, I would say that it's kind of the social self. And also the helping others also require the abilities of the social self. Yes.
What's the earliest that an infant can identify their own agency somewhere in their sensory field? Like moving a hand in front of their eyes and then understanding that they should change how they move their hand or something like that. Developmentally, what's the earliest that they use self-generated action to learn?
There are types of the action that infants can produce. For example, the hand regard is regarded as one phenomenon that infants can show. So observing its own hand, they seem to learn their contingency between the brain activities and then the outcomes of the visual experiences.
Yeah, that's because I guess what I'm getting at is if you say that when they see in the mirror, it takes longer for them to learn, but if you show them something directly, it's earlier. It suggests to me the thing that is changing is their ability to identify more complex contingencies. But maybe as early as they look at their hand like this, they already are doing that kind of task, just a much simpler version of it.
Yeah, sure. And so not only these two phenomena, but also there are many cognitive behaviors which require consciousness or self-cognition and so on and so on. But then if you just look at these behavioral levels, you see there are inconsistencies between their behaviors. They have the different ages to show their abilities and also the different requirements for it. So it's just pieces of puzzle in the findings of the developmental psychologists. And what we have been suggesting is that their unified theory, which may provide the big picture of the development, can be explained by predictive coding. So here, what we want to know is that what's the core, the neural mechanism for the cognitive development in infants. And we have been suggesting that the predictive learning or predictive coding may account for their various various dynamics of the development. Here I give you the very simpler definition of the predictive coding. So our body, the sensory motor system, act on the environment, which first receive the motor command from the brain and also the kind sensory input from the sensory state. And then after acting on the environment, the body receives the sensory feedback as an actual sensory signal. And what the brain does in parallel with this process is that the brain learns to acquire the predictor, the internal model, which simulate the sensory actions in the environment. The predictor receives the inference copy of the motor command and also the current sensory state, and then they anticipate their predicted outcomes, their sensory state at the next step. And what predictive learning does is to minimize the prediction error, which is calculated as a difference between the actual sensory feedback and the predictive sensory feedback. This is a simple definition of the predictive coding. Or when I focus more on the developmental process, I say that it's predictive learning rather than coding. And what we have been suggesting is that the minimization of the prediction error is mainly achieved in the two ways. The first way is to update the predictor itself. Of course, the infants are born with immature capabilities, so they cannot properly predict their outcomes of their sensory motor actions. So the predictor, it can be a model like a neural network model or a Bayesian model that should be updated first in order for the brain to properly predict their actual event. And then the second process is to utilize the predictor in order to act on the environment. So the predictor, the important point is that predictor is used not only for generating on action, but also for reacting on the other persons. Especially in their very beginning, there you have seen that their young babies already help other persons. And development psychologists suggest that the infants already have their abilities to, for example, estimate the internal representation of other persons or the desires of other persons. That's why they can help other persons. But here our suggestion is that maybe the infants may not have the abilities to distinguish the self from others, or even they don't have the ability to estimate the other person's intention, but they just apply their own internal model to predict what happens in the environment. So they may not have their kind of consciousness about the self or differentiation between the self and other yet, but this unified representation of the self and other may enable the infants to act on the environment as a social agent, which is their origin, which becomes the origin of their social behaviors. And to verify this hypothesis, we have designed several models. And this is the one model which reproduced the development of the prediction of the other person's intention. And here we use the autoencoder, just the Knaisan introduced. So in this experiment, the robot has experience to reach for the target. It's a very simple task. And through this action, the execution, the robot learns to integrate their visual, tactile, and motor signals into the autoencoder. Here the point is that, of course, the autoencoder has smaller dimensions as the middle layer. So, which means that the neural network has to abstract the input signals. And what we expected from this experiment is that through this large model, their predictive learning, the robot would acquire a kind of their internal representation, like a symbolic representation of the actions, which may correspond to the qualia of the action. In the morning, we discussed that how we acquire the qualia and also how it represents or corresponds to the consciousness. And we can say that the representation acquired in the predictor may correspond to the qualia for the actions, the patterns of the actions. And interestingly, these autoencoders allows the robot not only to produce its own behaviors, but also to estimate the other person's behaviors based on this qualia. The important thing is that the autoencoder integrated the multimodal signals into one network without any distinction between them. So because of them, the network can predict not only their visual signal, but also the other signals. So in the case of the robot observing other persons or other robots' behavior, this blue robot, which learned to integrate the multimodal signals, can only receive the visual signal, because the blue one is just observing the green robot. So in this case, the blue robot receives only the visual signals. But this network enables the robot to predict not only the visual, but also the tactile and the motor signal, which are associated in the network. So the representation in the middle layer, which may correspond to the qualia, allows the networks to predict the visual and tactile, the imaginary signal in the brain. And these imaginary signals can be used as an imaginary input to the network. So using this imaginary loop in the network, the robot can simulate what would be their next state of their current actions. And by continuing this loop, the robot can predict the further steps in their actions. And using this model, we have designed how what's the role of the internal representation of the autoencoder. And first, we observed how nicely the image is predicted. Here, the one assumption was that the robot, we did not differentiate the perspectives between the self-robot and other robot. So that when the robot observing the other robot, the robot can take the same perspective with the self. So that's why the predicted image looks quite similar to the actual image. And then we classify the predictions into the correct prediction or incorrect prediction and so on to see how the cognitive abilities for estimating the other person's intention gradually emerges in the network. This is the result. The important graph is the left one. So if you look at the green bars, you can see that their correct prediction gradually there increases, which means that over the learning, the network gradually acquire their internal representation of the actions, the couriers of the actions. And of course, we look at not only the behaviors achievement, but also the internal representation in the network to see how their actions are represented in the network. And this is their representation from the left experiment. Here, there are 3 lines which corresponds to the 3 actions in the region behavior. And you can see that the representation, the internal representation are nicely structured in the network, which indicating that there are 3 actions, 3 different actions are well structured while keeping their similarities or the correspondences between the actions. And not only their motor behaviors, but also the emotional the expressions can be trained using their predictive coding. And in this experiment, we designed a large model, the restricted Boltzmann machine. And this network learns to integrate the visual and the audio signals into the higher layer. Again, what we expected is that the highest layer, which has the lowest dimensions of the neurons, would acquire some internal representation here corresponds to the emotion, because as we input their emotional related signals, like a visual, the smiling face, or the hand movement, and then the speech signals. And then, so we observed again the internal representation of the network in order to see how the emotions is represented in the network. Again, it might be related to the courier of the emotion. This is a result. This is their principal component analysis of their highest layer. Actually, the highest layer have the 50 neurons, and we applied their principal component in order to see in the 2 dimensions. And you can see that these colors correspond to the different emotional state. So the patterns of the emotions are now nicely represented in the network. And then the interesting thing here again is that similar to the previous experiment, the network also showed the abilities to predict or to better estimate the internal state by generating the imaginary the perceptual signal. In one experiment, we provided only the audio signal as an input. The network has the 3 types of input. There are 2 visual input, the facial expression and the hand movement, and the 3rd one is auditory. And in this test, we provided the auditory signal as an actual input, and then observed how the network can internally generate the visual signals through their internal representation of the network, and how the predicted signal, the imaginary generated signal, help the estimation of their internal state of the emotion. So this is their very first estimation of the emotion. So here the truth value is here. So the first estimation using only the audio input is quite far from their truth value. But then by repeating their internal, their imaginary their predictions of the sensory signal, you can see that their prediction of the estimation of the emotional state gets closer and closer to the truth value, which suggesting that the internal representation, their abstract, the representation of the sensory signals allows the network to better predict their other person's internal state by generating the imaginary sensory signal through the network. Again, this is not directly about the consciousness, but then you can see that what we can do with the predictive coding in the robot modeling, and how this kind of model might be used for examining their abilities or the role of the consciousness or their couriers in the network model.
In that case, what is the role of motor, not the sensor, in the robots?
In the second experiment, we did not directly use the motor signal. It's only about the merge model, the merge sensory systems. In the first experiment, the robot acts on the environment, and then this action is perceived as a proprioceptive signal.
So it sounds like very much pattern recognition, but what is the difference between such pattern recognition process and this?
I think the motor experiences allows the robot to have their, a bit redundant representation or redundant signals from the actions.
But if imagine the robots can smile and can angry and something, and when the robot sees the smiling and then anger or something, so such kind of discommunicating robots, then maybe such a result transform or.
Yes, in this experiment, the robot just received their signals and then learned it, so it did not have the real-time interaction. But in the extension of this study, we designed their active inference model. So the robot tries to extract their signals from the other persons by acting on them, reacting to the
I think
persons.
this difference between these experiences is more important.
Yeah, thank you.
In the first experiment, what is the importance of this perspective? So you just match the perspective completely same to your action, other action. But if you look into the baby's example, the perspective is completely different, right?
Yeah.
So does it generalize the different perspective in your experiments?
What we currently assume is that the inference already have the abilities to have the correspondence between the different perspectives. For example, by looking at the similarities between the body structure and something, the robot can, or the inference can also calculate the different perspectives. This is one big assumption in our current model. And actually this assumption is quite strong because once we provide a bit different perspectives to the robot cannot well predict the image or the motor signals, but as we use the raw images currently. But if the robot could extract like in a hand posture or the position of the object instead of using the raw image, maybe it might be possible to apply the same ideas for this new model.
So in the developmental psychology literature, so there's a famous what is it? I don't know how to say in English, but mountain of the perspective learning of babies. Yeah. So is it very early in the stage compared to the?
I think they're about 18 months old or something. They can pass such a perspective taking task. It takes time to acquire such an ability.
Thank you.
Okay, so this is the first part of my study, and the second part I would like to talk a bit about the autism spectrum disorder. So based on this predictive coding idea, we try to also understand what different consciousness or what different cognitions that ASD persons has. And let me give you one example. So you can see letters on the slide. What letters, what alphabets can you see here? There is no trick, it's very, very simple task.
S.
S, yes?
H.
H, yeah, thank you. The question is, which letter comes into your mind first? S or H? S. In their study about the ASD, they have shown that the people with ASD tend to first look at the local letter.
We're just sitting too close.
Yes. Good good excuse. Yes, of course, depends on how far from the slide or how the letters are described. But in their cognitive experiment, the researchers shown that the ESD persons tend to look at the local features rather than the global features, whereas the TD persons tend to look at the global picture rather than the local features. Of course, you can switch between them. And another example from my colleagues in the University of Tokyo, she actually is diagnosed as Asperger's syndrome. And she said that she has difficulty in recognizing the hungriness. It was very surprising to me because without any effort, I can easily realize hungry about 12 p.m. or something. But she said that she first equally perceived the much modal senses, like, for example, the itchy scalp or chest discomfort or something. So she cannot easily realize whether she is hungry or not. And she said that she has to carefully and very closely look at her senses and then consciously integrate or ignore some senses. And through these processes, she can finally realize whether she is hungry or not. She said that she sometimes forgets about the hungriness, or she never realized the hungriness, and she falls down because she cannot eat anything. So the question is why she has the difficulties in recognizing the hungriness. So from this experience or the report, I realized that of course the humans do not have any sensor which can directly sense the hungriness. Like for example, the brightness of their environment, our sensors in their eyes can directly measure it. But in case of the hungriness, we don't have any sensor which directly measures the hungriness. So we also take the same processes. First, we realize that, okay, we don't have enough power to stand, or my stomach is moving or something. And then by integrating these sensory informations, we finally realize the hungriness. So it seems that the people with ASD does these processes in a conscious way, whereas the people with TD automatically does it. It's like an emotional recognition. In case of the emotional recognition, we can quickly realize we are happy or we are sad or we are naive or nervous or something. But then there are people with ASD have similar problem in the the emotional recognitions. So the question is how this kind of their different levels of their consciousness may occur. And to answer this question, I'd like to introduce one interesting robotic model which has been developed by the Professor Jun Tani. And he designed the multiple timescale recurrent neural network. The recurrent neural network has multiple layers, and each layer has different timescale. For example, the lower layer has a shorter timescale, which remembers only the short time information. And the higher layer has longer timescale, which enables the networks to remember the longer timescale. And based on using this network model, they have first shown that the robot can learn some multiple steps of their actions. For example, they're picking up the box and then moving the box up and down 3 times, and then moving the box left and right. So this kind of different action primitives can be coded in the one network, and then the higher layer of the network can control which action primitives should be executed. But then once they introduce the noises in the network, so they somehow disconnected the higher layer and the lower layer, they found something like their schizophrenia-like behaviors in the robot. Once they introduced their noises, for example, the one robot produced one robot could not move or could not reproduce the repetitive motions like this, or another robot produced forever the repetitive motion. It's like an ASD person's repetitive behavior. So this is just one example, but then we suggest that this kind of the hierarchical mismatch or the imbalance between their top-down prediction and the bottom-up recognitions may produce there are this kind of the developmental disorders. So we intend to further investigate what kind of their disorders in the network may result in their age-derived behaviors, as which we have shown in the previous slides. Okay, maybe there as the time closes, I will skip the one. So again, the same slide from in the beginning. So my take-home message is that we don't directly design the consciousness, but we believe that the consciousness, the functional consciousness may emerge as a byproduct of the cognitive development. And then the predictive coding is our powerful theories which generate the various types of various kind of their cognitive behaviors in robots. So I hope that our approach may also contribute to their better understanding the neural mechanism of the consciousness by looking closely at the representation acquired the network model. Thank you very much.